Quotient law and its applications. If a set of function is given and you are asked to find out whether its components are tensors or not, then how do you find out if a function is given? If it's a known function, then the direct method is to find whether the function transforms like the component of a tensor under the coordinate transformation, right? So for example, if you are given a rho lambda and you are asked to find out whether this is a tensor or not, okay, tensor or not, how do you find out? The direct method is to write the transformation. And you have to see whether the components of this tensor will transform according to the law of transformation of the tensor, right? But what if the functions are unknown? For example, I have a function a and I don't know whether it is covariant or contravariant. I don't know anything about the function. A is an unknown function. Then how do you find out? I only know a is a function of, for example, alpha or beta or gamma, something. That's it. I don't know whether it is alpha is covariant or contravariant. I don't know anything. Okay. So this is an unknown function. A is an unknown function. Then how do you find whether it is tensor or not? That is a question. So the quotient law provides a simple alternative to this issue. The quotient law states that if the inner product of a function, of an unknown function, with an arbitrary tensor is a tensor, then the unknown function is a tensor. Okay. So quotient law states that if the inner product of an entity, here this entity is the unknown function. Okay. This entity is the unknown function. So quotient law states that if the inner product of an entity with an arbitrary tensor is a tensor, then the entity is a tensor. Okay, so for example, I am going to take A alpha beta gamma. Let A alpha beta gamma be an unknown function. Then we choose an arbitrary tensor. We have to choose an arbitrary tensor and I have to take the inner product. Okay, so we are going to choose. Okay, we choose an arbitrary function, arbitrary tensor B beta sigma gamma. Okay, this is known tensor. This is known. So this is known arbitrary tensor. Okay, so A alpha beta gamma is an unknown function. Now we choose an arbitrary tensor B beta sigma gamma such that, okay, so we choose this arbitrary tensor in such a way that there is at least one contravariant and one covariant index. At least one contravariant and covariant index. So this arbitrary tensor should have at least one contravariant and covariant index. So in such a way, we choose a arbitrary tensor. Now we have to take the inner product of this unknown function and the arbitrary tensor. A, alpha, beta, gamma, B, beta, sigma, gamma. So let this inner product be C, sigma, alpha. So we know that inner product means you have to take the outer product and then contraction, right? So therefore for contracting, I am writing here gamma and here gamma. Here beta is there, here beta. So anything you can use for the contraction operation. And after contraction, the rank will reduce. Rank of the tensor will reduce. So here I have taken rank 3 tensor and here I am getting rank 2 tensor. Rank 3, rank 2. Okay. So that's how I choose the arbitrary tensor. Now, the inner product of the unknown function and the arbitrary tensor gives a tensor. If it gives a tensor, then A is also a tensor. Okay, if this inner product does not give a tensor, then A is not a tensor. That is how you check whether the given unknown function is tensor or not. So the quotient law states that if the inner product of an entity with an arbitrary tensor is a tensor, then the entity is a tensor. Otherwise, it is not a tensor. Okay, that is known as quotient law. Now you have to prove quotient law. Now, in order to prove the quotient law, I have to write the transformation for both A and B. So I don't know whether A is a tensor or not. Therefore, I am not writing A prime. I am just noting A bar. A bar of mu lambda rho. Okay, I'm just denoting it by A bar. A bar is nothing but the transformation of A. So A, alpha, beta, gamma is transformed to A bar. Okay. Similarly, the transformation for the arbitrary tensor also I have to write. So I am denoting B bar lambda theta rho is equal to partial derivative of x prime lambda x beta. For example, this is going to be beta sigma gamma. Okay. Then partial derivative of x prime theta with respect to x sigma, partial derivative of x gamma with respect to rho, x prime rho. Okay, so this is the transformation for A and this is the transformation for B. Okay, now I have to multiply. After transformation, I am going to take the inner product. Okay, so the inner product after transformation will be multiplied by theta rho, right? So I don't know the transformation of A bar. Therefore, I will write it as it is. Okay. And for B bar, I have this transformation. Now, even after transformation, it should give a tensor, right? So tensor, what is the property of tensor? Even after the transformation, the tensor nature should not change. So if A, the inner product of A and B is a tensor, then even after transformation, that is A bar multiplied by B bar, you should get C bar. Okay, let this be theta and mu. Okay. Now I can, and see if this is C bar, then I can define C bar also. C bar theta mu is equal to partial derivative of, now let this be C sigma alpha in the other coordinate system. Okay, dx sigma partial derivative of x alpha x prime mu. Now I have to substitute it in the main equation here. Here I am going to substitute. Okay, so a bar I have no idea, so I'll just write a bar multiplied by b bar. B bar is this one, right? So I'll substitute b bar here. So partial derivative of x prime lambda with respect to x beta, partial derivative of x prime theta with respect to x sigma, partial derivative of x gamma with respect to prime rho, b beta sigma gamma. Okay, this is equal to, now C bar, partial derivative of x prime theta with respect to x sigma, x alpha with respect to x prime mu, and C sigma alpha. Okay. Now I'll give some name for these equations. Okay, let this be equation 1, and let this be equation 2, and let this be equation 3. Now we have to solve all these equations. Okay, we have to solve all these equations and you have to find a bar. To solve this equation, first I multiply equation 1, multiply equation 1 with partial derivative of x prime theta, this quantity. Okay, why I'm going to multiply with this quantity? Because in equation 1, on the right hand side I have C sigma alpha. Okay, and in equation 3 also I have C sigma alpha. So if I multiply this quantity to equation 1, then the right hand side of equation 3 and equation 1 will be equal, and it will be easy to simplify. Okay, so I multiply equation 1 with partial derivative of x prime theta with respect to x sigma, partial derivative of x alpha with respect to x prime mu. Then equation 1 becomes, on the left hand side you have a alpha beta gamma, partial derivative of x prime theta. So both left hand side and right hand side I have to multiply with this quantity. Partial derivative of x alpha with respect to, and b is already there on the left hand side. And on the right hand side also I multiply with this quantity. And C sigma alpha is already there. C sigma alpha. So this is equation 1 after multiplying with partial derivative of x prime theta with respect to x sigma and partial derivative of x alpha with respect to x prime mu. Now let this be equation number 4. So if you see equation 3 and equation 4, the right hand side are the same. So what I do is that I'm going to subtract 3 minus 4. Equation 3 minus equation 4. So the right hand side will become 0 because the same quantity is there, right? So right hand side will become 0 and the left hand side I have to subtract a bar of mu lambda rho, partial derivative of x prime lambda with respect to x beta, partial derivative of x prime theta with respect to x sigma, partial derivative of x gamma with respect to x prime rho, b beta sigma gamma minus a of alpha beta gamma, right? Alpha beta gamma, partial derivative of x prime theta with respect to x sigma, partial derivative of x alpha with respect to x prime mu, b beta sigma gamma is equal to 0. So you'll get a equation like this. Okay. So this quantity minus this quantity is equal to 0. So here we can take certain terms common, right? What are those? We'll take it. For example, I can write mu lambda rho partial derivative of, from here I think I can take b beta sigma gamma common outside. Okay, so prime theta gamma minus alpha beta gamma, partial derivative of x prime theta, partial derivative of x prime mu multiplied by b beta sigma gamma is equal to 0. Okay, so b I am taking outside. Now, if this entire equation is 0, then it means that either b has to be 0, otherwise the entire quantity in this bracket has to be 0. But we have taken b beta sigma gamma as an arbitrary tensor. So that which we have chosen, therefore it cannot be 0. If it is 0, then it will lead to a trivial solution. Therefore, the quantity in the square bracket must go to 0. Okay, so this quantity in this square bracket must go to 0. If that is the case, then I can write a bar mu lambda rho partial derivative of x prime lambda x beta partial derivative of x prime theta sigma partial derivative of x gamma with respect to x prime is equal to a of alpha beta gamma partial derivative of x prime theta with respect to x sigma partial derivative of x alpha with respect to x prime mu. So here we can cancel these terms and I can take these two terms to the other side, right? So I can write a bar mu lambda rho is equal to partial derivative of x alpha with respect to x prime mu, then partial derivative of x beta with respect to x prime lambda, this quantity, this going to the other side, right? Then I can write partial derivative of x prime rho with respect to, this is x prime rho, with respect to partial derivative, with respect to x gamma, partial derivative of x prime rho with respect to x gamma, right? Then a is also there, a alpha beta gamma. But this is looking like a law of tensor transformation, right? See, if you closely see, here a bar is in the transformed coordinate, a is in the old coordinate system, and this represents a transformation. And here you can see this one is covariant index, and here this is also covariant, this is contravariant. Okay, so but this is looking like a law of tensor transformation, and looking at the structure of this transformation, I can write this as, how do I write? So two covariant and one contravariant. So I have to write. So now instead of a bar, I'm going to write a prime because it's tensor. Rho, mu, lambda. Here rho is contravariant, right? And these two are covariant. So mu and lambda are covariant. So this is the tensor. So how can I write this one? I can write it as rho mu lambda is equal to partial derivative of x alpha with respect to x prime mu, partial derivative of x beta with respect to x prime lambda, partial derivative of x prime rho with respect to x gamma, and a gamma alpha beta. Okay, so this is how we get. Okay, so the quotient law states that if the inner product of an entity with an arbitrary tensor is a tensor, then the entity is a tensor. Now we have proved the quotient law. So if you have an unknown function, then how do you find whether it is a tensor or not? So you have to take an arbitrary tensor B, and you have to take the inner product of A and B, and if it gives a tensor, then A is a tensor. Okay, so we have proved the quotient law. Now we have to see the application of quotient law. Application of quotient law. First one is the metric tensor. So the fundamental application of the quotient law is regarding the metric tensor. So we know that the metric ds square is equal to g mu nu dx mu dx nu. Okay, here this ds square is a tensor of rank 0 because it is a number, right? ds square is a tensor of rank 0. Okay, and dx nu is a contravariant tensor of rank 1, right? Contravariant tensor of rank 1, and dx mu is also contravariant tensor of rank 1. So this outer product, right? This outer product must be a contravariant tensor of rank 2, right? This outer product must be a contravariant tensor of rank 2 because outer product means just the rank will increase, right? So dx mu and dx nu, if I take the outer product, then the result will be a contravariant tensor of rank 2. And on the left hand side, we know ds square is a tensor of rank 0. Okay, therefore, according to the quotient law, the product of, so g mu, suppose we don't know g mu nu. Okay, so this is the unknown. this is unknown, this is arbitrary tensor, arbitrary tensor. And now we know that if you take the inner product of these two, then the result is also a tensor of rank 0. So result also we know. So unknown function taking inner product with an arbitrary tensor, and the result is also a tensor. Therefore, G mu nu must be a tensor. Right? And now we know that from quotient law, G mu nu must be a covariant tensor of rank 2. Only then I can take the inner product, because we have to equate one covariant index to another contravariant index, right? Therefore, G mu nu must be a covariant tensor of rank 2. Okay. Then according to the quotient law, the product of any arbitrary tensor with a given function is a tensor, then the given function is also a tensor. Hence, the quantity G mu nu must be a tensor of rank 2, and this is called the fundamental metric tensor. Or more precisely, I can call it the fundamental covariant metric tensor. Okay. So it is a fundamental covariant metric tensor of rank 2. G mu nu must be covariant. Therefore, whatever metric tensor you are getting from the line element must be covariant. Okay, in four dimension, G mu nu can be represented as G00, G01, G02, G03, G10, G11, G12, 20, 21, 22, 23, 30, 31, 32, 33. This is the fundamental metric tensor in 4 dimension. Now, here this G mu nu may be a function of x mu. It can be a function, and sometimes it may be a constant also. Okay. So the only restriction is that the determinant of G mu nu should not be equal to 0. Which means that G mu nu must be non-singular. If it is 0, if the determinant is 0, it is called singular. So we say that the determinant of G mu nu should not be equal to 0, and G mu nu must be non-singular. That is the only restriction to the fundamental metric tensor. Okay. Then the corresponding space is said to be Riemannian. Then the corresponding space is said to be Riemannian. Okay, so G of mu nu should be a function of x mu, and determinant of G mu nu not equal to 0, then the corresponding space is said to be Riemannian. Now, if all the elements of G mu nu are independent of x mu, if all the elements of G mu nu are independent of x mu, for example, Minkowski space, right? Then G mu nu will be, it will have only the diagonal elements, right? 1, minus 1, minus 1, minus 1, and all the other elements will be 0. So that is independent of x mu. It's not a function of x mu. It's just a constant. 1, minus 1, minus 1, minus 1. All the other elements 0, right? Then the space is called Euclidean. Then the space is called Euclidean. If G mu nu is a function of x mu, then it is a Riemannian space, and G mu nu are independent of x mu, then the space is called Euclidean. Okay. So this is the first application of quotient law. Now we go to the second application. Reciprocal tensors. Now, two tensors A mu nu and B nu lambda are said to be reciprocal to each other if their inner product is equal to unit tensor. Okay, so if I take the inner product of A mu nu and B nu lambda. So inner product means first you have to take the outer product and then do the contraction. So for doing contraction, here see one contravariant should be equal to covariant. Okay. So two tensors A mu nu and B nu lambda are said to be reciprocal to each other. If they are reciprocal to each other, if I take the inner product, I should get the unit tensor, right? Unit tensor. If I get unit tensor, then A and B are called as reciprocal to each other. A is the reciprocal of B and B is the reciprocal of A only if the inner product of A and B gives unity. Okay, so we can define the fundamental contravariant tensor G mu nu as the reciprocal to the tensor G mu nu, right? Otherwise, I can write if I multiply G mu lambda, for this case I am taking G mu lambda and G lambda nu. If I take the inner product, I will get unit tensor. So here the elements of G nu lambda would be the G mu lambda and G lambda nu. These two should be reciprocal to each other. If they are reciprocal to each other, then I'll get unity. Okay, if these two are reciprocal to each other, then the elements of G mu lambda will be the cofactor of G lambda nu divided by the determinant of G lambda nu. Because you know the inverse is equal to adjoint by determinant, and adjoint is the transpose of the cofactor, right? So that's why I can write one as the cofactor by determinant of the other. In such a case, we can see that the tensor G mu lambda should be symmetric. Why symmetric? Even if I interchange the index G mu lambda and G lambda mu, the cofactor remains the same. Right? Therefore, if G mu lambda is symmetric, then G lambda nu should also be symmetric. So here we can see that if you multiply G mu lambda and G lambda nu, you will get unity. And also these two are symmetric to each other. So such tensors which are symmetric as well as reciprocal to each other are called as conjugate tensors. Tensors which are symmetric as well as reciprocal to each other are called conjugate tensors. Okay, so this is the second application, reciprocal tensors. First application was metric tensor. Now we go to the third application, raising and lowering operation. Now if A nu is an arbitrary contravariant tensor, then its inner product with the tensor G mu nu will be an arbitrary covariant tensor because of the contraction, right? So if I take the inner product, it will be, see here there is nu, here there is nu, okay, nu and nu. So if I take the inner product, then I have to get an arbitrary covariant tensor because of the contraction. Then I'll represent it by A mu. Okay. Similarly, what will happen if I multiply the G alpha nu? Here it is contravariant multiplied by A mu. So I am writing G alpha nu as it is. A mu I can substitute A nu G mu nu, right? So A nu G mu nu. See here I can change the order. Okay, there is no issue. So I can write G mu nu first and then A nu. There is no issue. Then you can see here there is nu and nu. Therefore, this will be unit tensor, fundamental unit tensor multiplied by A nu. So unit tensor means alpha equal to nu. This will be 1. Therefore, A nu. So here you can see if I multiply the covariant metric tensor with a contravariant tensor, you will get a covariant tensor. And here we can see if I multiply the contravariant metric tensor with a covariant tensor, then I will get a contravariant tensor, right? So here the metric tensor act as a lowering operator. Okay, so here this contravariant is becoming covariant. So this is lowering operator. And this operation is called lowering operation. And here you can see, if I multiply the contravariant metric tensor with a covariant tensor, the resultant tensor is contravariant. So this is raising operation and this operator is called raising operator. Thus, the indices of any tensor can be lowered or raised by forming its inner product with either of the fundamental tensors. So you have to note that without a fundamental metric tensor, a covariant vector cannot be converted into a contravariant one and vice versa. Okay, so that is the importance. The indices of any tensor can be lowered or raised by forming its inner product with either of the fundamental metric tensor. Without a fundamental metric tensor, a covariant vector cannot be, a covariant tensor cannot be converted into a contravariant one, and vice versa. So that is the importance of the quotient law and its application, and the fundamental metric tensor. Okay, so today we will stop with this.